All right, well, welcome back to another day of vector calculus. The plan for today is to keep talking triple integrals. We're going to keep talking triple integrals for a while. But today what we're going to do is we're going to look at how we change or how we can change to other coordinate systems, like we talked a little bit about cylindrical last time. I think I'll do another example to kind of remind you about that. And then we'll turn our attention to spherical, see how that gets changed or how we do that change. And then we'll start looking at some more applications of these higher order integrals, like other things that we can do with them. So that's the plan. But I do want to start, as always, offering up, looking at homework. So any homework questions people would like to look at? All right, so Seamus already threw out here from 5.4, numbers 8 and 11. And Eduardo, I see you put 5.4. Was there a specific number? Oh, I got it. I see it. It's earlier. Never mind. Yeah, I got it. Number 9. Number 11. Okay, so I'm going to guess that 8, 9, and 11 are all kind of similar, but we'll take a look at those and at least do a little bit of them. So Matt, you were just chiming in. Were you just letting me know that I was blind and didn't see the other?
Yeah, sorry.
Yeah, no, that's all good. I appreciate that. Okay, well then let me go ahead and pull that up. We'll look at 8, 9, and 11. So let me share my screen here. All right, so I've got number 9 up. Number 9 here says, find the volume of a right pyramid that has a square base in the plane. And then a vertex at 0, 0, 8, right? So that's number 9. Let's just see what the others are real quick. Number 8, we got doing a triple integral over the solid tetrahedron. Okay, so this is actually very similar to the one that we did in class. And then number 11, temperature, solid, bounded in planes given by this. Find the average temperature. All right, we can at least get them all set up. We'll talk about all of them. I don't know how far we'll go, but let's start with number 8 here. So number 8, we want to integrate the function minus 3x minus 8y. And we're bounded by the 3 coordinate planes and then the plane x plus y plus z equals 1. And so again, it's just evaluate that triple integral. All right, so let's go to the whiteboard. And for sure, the most important thing with any of these is to visualize the region where we're doing our integrals. All right, so let's start by drawing our coordinate system here. So there are our 3 dimensions, kind of like we've drawn before. Now, I did an example in class. I don't remember if that was on Friday or on Wednesday, but sometime last week. And this was the one where I used the 3, the corner in my room. So we had the floor was the XY plane, the whiteboard wall was the XZ plane, and the window wall was the YZ plane. And then the 4th surface that's forming the tetrahedron was a plane that was slanted down. So that's the one that I used my framed map to create. But basically, this is what we're going to see for our tetrahedron. So we're going to get a little triangular region here. But that other plane that was given by x plus y plus z equals 1, that's the one that forms that force side. All right, so to get this guy set up, again, we're going to be doing a triple integral. The function itself was, I think mine was minus 3x minus 8y. If that wasn't it exactly, well, that's close enough, because yours is probably going to be different anyway. And then we want to do a dv over this q. So again, for you D&D players, this is a D4. It's the four-sided die. And basically, we want to think about how to find that region. So far so good. Can you kind of picture it, I hope? All right. So now let's think about how we want to integrate, which order we want to do. I'm going to recommend that we do dz, dy, dx. Of the 6 different, this is my go-to. If all else is equal, I do this one, because this is how I'm used to seeing the world. We're used to writing functions as z equals, functions in space. We're used to writing functions in the plane as y equals. So it's kind of what I'm more comfortable with. So if we do this, then integration man is going to be walking around with his feet on the floor, and his head is going to be up here bumping against the roof, and the roof here is going to be formed by that slanted plane. So that means we need to take this equation and solve it for z. If you do that, you get 1 minus x minus y. So z equals 1 minus x minus y is the roof of that. The floor was the xy plane, so that's going to be 0. So as integration man is walking around in here, he's bumping his head against the roof, which is this plane, and his feet are always on the xy plane. All right, so before we go further, we good with this? Good so far? All right, I see a couple of thumbs up and mostly quiet, so I'll take that as we're good. All right, so now we need to think about the region in the xy plane over which integration man is walking. So I'm going to shade it in on my picture here, but it's this little triangular region that's on the xy plane. So let's redraw that like we're used to. Okay, so there's our x and y. And let me draw on the line. Okay, so that's this line right there. And so we're looking at this little triangular region, which means integration man in this case, if we do dy dx, it's going to be walking around like this. So we know that his feet are determined by, oops, sorry about that. His feet are determined by the x-axis. I erased too much. There we go. But then the question is, what about his head? Well, his head is given by this line. So what's the equation of that line?
Y equals minus x plus 1.
All right, so y equals minus x plus 1. And where's that come from, Bradley?
The plane. The equation of the plane.
Okay, so if you look at the equation of the plane and you let z equal 0, that gives you this guy right here. And the reason we can plug z equals 0 is because that's the xy plane. If you don't like that, the other thing you can do is figure out the coordinates of these vertices. And to find the points on the axes, it's really easy. You let the other two letters equal 0. So like on the y-axis, you let x and z equal 0, which gives us y equals 1. So this is up at y equals 1. For the x-axis, you let y and z equal 0. That's also 1. So now you can do your good old slope is -1, your y-intercept is 1. So you get negative x plus 1. All right, so there are the bounds then for y. And then the bounds for x, integration man is going to walk from x equals 0 out to x equal 1. So there's the setup
That makes sense, Bruce.
if we do dz, dy, dx. So just general recommendation, draw pictures. Draw the pictures, visualize this for the 3D. This is where the Play-Doh or other kind of modeling clay can come in handy. But the better you can visualize these regions, the easier it's going to be to set up the integral. Because now that we're here, this is a no-brainer, right? This is business as usual. You know what to do. And this is why, like I said before, and I'm going to probably say many other times, getting this thing set up is the majority of the battle. It's probably like 75 to 90% of the work is figuring out what your bounds are. All right, so is this good for whatever number this was? 8?
That's perfect. Thank you very much.
All right, you feel better? All right, good, Seamus. All right, any other questions on this one before we go look at number 9? All right, so let's go look at number 9. So we'll jump back to this guy. All right, so here's number 9. So find the volume of the right pyramid that has a square base in the plane, so between -1 and 1 for x and y, and a vertex at 0, 0, 8. So it says here, the graph shows a pyramid with a vertex at 0, 0, 3. So ours is taller, but with the same square base. Okay, so then round your answer to 4 decimal places. Well, that seems pretty easy enough. If we want to find the volume, that just means that we need to do a triple integral of 1. So let me clear all this stuff. But basically, we want to do the integral over that space, that volume in space, of 1 dV. So again, really the issue is what are the bounds and everything. All right, well, as always, let's draw pictures. So I'm going to start by drawing the picture in the XY plane. Because what we were told is that the base of this thing is a square. Looks like that. We were told we go from -1 to 1. So I'll just mark that one as 1, 1. And this one is -1, -1. But so we're looking down on the pyramid right now, right? Imagine we're flying over the pyramid, looking down on it. We see that. So what we would see with the rest of the pyramid would be that, right? So if we're looking down, we can see the 4 different faces. They all look triangular, right? But from above, this is what we see. All right, so far so good. Okie dokie. So
Yes, yes.
here's what we should do. For this one, we should really split it into 4 pieces. Because integration man, as he's walking around, right? Remember, he's walking around this square. His feet are always on the XY plane, but his head is going to be bumping up against the slope of the pyramid. And depending upon where he is, he's hitting a different piece of the pyramid. So what we really need to do is break this into 4 different integrals. okay, where we're going to look at each of these four sides as one single integral. However, we're going to be smart about this, and we're going to notice that the function that we're integrating, which is just 1, is going to be symmetric no matter where we are. So we can definitely make use of symmetry and do just one of these things. And if we just do one of the regions, then we can multiply it by 4. But again, that's only because this function is nice. It's just 1. Otherwise, we'd have to set it up as 4 different integrals. Okay, so you know what I'm going to do? We'll actually do it kind of both ways. We'll get it set up both ways, just so that you can see what the approach would have to be. But for the sake of doing one of the let's number the regions. We'll go, this is face number 1, face number 2, face number 3, and face number 4. So let's look at number 1 first. So we're going to do 4 times the integral over number 1. Okay. So I'm going to call it Q1, Q equals 1. All right, so we need to, again, decide what order we want to do the integration. I'm again going to suggest dz, dy, dx. Because like, for example, the dz's, I already know that his feet are on the xy plane and his head is going to be on whatever this plane is. We'll figure that out. But then for the dy dx, we're really looking at integration man just in this triangle right here. And so for the y's, integration man in here, like there's an integration man, here's a little shorter integration man. Notice that his head is always on this diagonal line, the one with the positive slope, and his feet are always on the one with the negative slope. So what are the equations of those lines?
Y equals X and negative X.
Okay, so the positive one is y equals x, so that's his head, and his feet are at y equals negative x. And then the bounds on x, they're going to go from 0 to 1. So just from this picture alone, we could already set up the dy dx bit. So notice the only thing left is we need the ceiling function, right? We need to know what is that surface that defines the top of this pyramid. Well, that's a plane. Because it's a plane, we find its equation by taking 2 vectors in it and crossing them. So let's start with some points in that plane. And I didn't need for that to be a vector. I want that to be a point. Okay, so let's think about some points in this plane. We know we've got
1, 1, 0.
1, 1, 0, good. So Victor, you started as 0, 0. That's going to be the vertex, the point that's up above, right, the tip of the pyramid, when x and y are 0. And mine was, they told me the vertex was 0, 0, 8. So that's the point that's up there. And then we have one more point that's down here at the bottom.
1, negative 1, 0.
There you go, 1, negative 1, 0. So those are 3 points that are on that face. Alternatively, we could have used, say, this point down here. The point that's 1, 0, 0. That's also on there, right? We have all kinds of different options, but all we need are 3 that are not collinear, so this is enough. So now let's find 2 vectors that connect these guys. So for example, to go from 1, 1, 0 to 0, 0, 8, I'm going to have a vector -1, -1, 8. So that's the one that's connecting this point on the bottom and this point at the top. If you're at the top, or sorry, at the bottom, you'd have to go down 1 and left 1 and up 8. Okay, similarly, like for these two, to get from 0, 0, 8 to 1, -1, 0, that would be 1, -1, -8. And so that's the vector that is this side. We could have used 1, 1, 0 and 1, -1, 0 and gotten this line as a vector. That's cool too. It doesn't matter. You just need two of them. But now what we're going to do is we're going to cross these. Because when you cross two vectors in a plane, you get the normal vector to that plane. All right, so here's our I, J, and K. So let's just see what we get when we do that cross product. We're going to get 8 minus -8. So that's a 16. For the J's, I'm going to get 8 minus 8. So that's 0. And for the K's, I'm going to get 1 minus a -1, which is 2. Okay, so this is a normal vector. But I'm going to help ourselves out a little bit. Just make numbers smaller. I'm going to go ahead and divide that by 2. But now that I've got that normal vector, I can start creating the equation for that plane. It's going to be 8x plus 0y plus 1z equals some number. So the 8, 0, and 1, that came from those. And then to figure out what this number is, I'm going to plug in one of the points. So for example, if I were to take the 1, 1, 0 and plug it in, I'm going to get 8 plus 0 plus 0 equals this number, or that number equals 8. So the equation of my plane is 8x plus z equals 8. So that's the plane that forms this side over here. So I need to solve that for z. And so as a z equals, that ends up being 8 minus 8x. So without the 4, that integral is finding the surface under face number 1. But because we're just finding volume and this thing is symmetric, I know that my total volume is going to be 4 times that. And again, now that we're here, it's, well, just do the integral. All right, so, okay so far? All right, now, this we're making use of the symmetry, but suppose that we don't have the symmetry. And this is actually important for the next question, number 10, because number 10 is similar, except they tell you to integrate some function over this volume. And I didn't look closely enough, so I don't know if it's symmetric, but it's very possible that it's not. So the other option then would be to do the integral over surface 1 plus the integral over surface 2 plus the integral over surface 3 plus the integral over surface 4. And we would basically have to do this same kind of process for each one of them. Also notice that the triangular regions over which integration man is going change, right? Like if we look at number 3, for example, his head is now at y equals negative x and his feet are at y equal plus x. So these bounds would be swapped and the x's would go from -1 to 0. But then the surface isn't 8 minus 8x anymore. So you'd have to find the equation of this plane. It probably is not going to surprise you that from symmetry, it's 8 plus 8x. But then you could do the same thing for 2 and 4. But for 2 and 4, I'm going to definitely suggest that instead of dz dy dx, you do dz dx dy, because that way integration man is sideways. Because if you do integration man vertically here, you'd have to do 2 separate integrals. All right, so this one gets complicated because there are actually like 4 surfaces, right? There are 4 surfaces that integration man is on. And so it's a little bit more challenging. Turns out you could turn it into 2 integrals if instead of doing a dz first, you did either a dy or dx first. But it's a little bit harder to visualize, so it's probably worth it just to suffer through setting up more than 1 integral. All right, so I don't remember who asked about number 9. I think that might have been you, Eduardo. Is that better? Yeah, okay, cool. All right, so lastly, let's go take a look at, it was number 11. So let's go see what that one's asking us to do. Oh, by the way, so here you can see here's number 10. So it looks really similar, but now the function that we're integrating is x squared. So you got to be a little careful with symmetry there. So
Oh, it's not symmetrical.
yeah, like to use symmetry, you have to prove symmetry, and by the time you prove symmetry, you may as well have just like done it, right? Set it up with the 4 pieces. All right, so let's lastly look at number 11. So number 11, temperature in this solid, which is a tetrahedron again, it's given by this formula. They spelled Celsius wrong. So we got that formula in degree C, and we want to find the average temperature. All right, now I've not talked about average values. This is definitely one of the applications of triple integrals, is to find averages of volumes, or over volumes, I should say. Just like a double integral can be used to find average over a region in the plane, just like a single integral can find the average value over an interval in xy. So it really is the same idea as before. We just have to extend it. So let's go back to just average value. Let's say you got an f of x, and you wanted to find the average value. Do you remember how to do it?
Don't you just use Don't you just integrate it and use the fundamental theorem?
Okay, so you integrate from a to b, f of x dx. But then there's one more thing you got to do to it to get the average value.
Divide by b minus a.
Yeah. Remember with averages, in general, it's you add them all up and then divide by how many you have. Well, that's what this does. It's adding them all up. That's what integral does. So it adds up all the function values. And then we divide by the interval because that's how many x's we had, basically. So that's the 1D case. If you go to the 2D case, so this time I have to say f of x, y on some region, then the average value is going to be, again, the double integral over the region. So you're going to add it up over that entire region. And then we have to divide by what? What do you think it is we divide by here?
Our last bound on our double integral.
Okay, that'd be a good guess because that's that same as that b minus a. But that doesn't get to all of the values. And Victor just put in the chat box area, and that actually is what we need to divide by. Because if you think about it, we're adding this up over an entire region. If we divide out by the area of the region, we're getting that value basically at each of the one little dots. So we went from a one-dimensional interval to a two-dimensional area. Okay, so now let's extend it to 3D. All right, well now we're going to do a triple integral. And what do you think we divide by?
The volume.
Yeah. All right, so that's how we can deal with average values. And like I said, this is one of the applications of triple integrals, is finding the average value over some solid area. So you think about this problem, we were told how temperature is distributed. What we're going to be able to do is, using that triple integral, we're going to be able to calculate the average temperature in that space. And you don't have to think very hard, I doubt, to come up with an idea of where that would be useful or why someone might care about average temperature in a given volume. All right, well, let's do that for this specific one. So let me erase this stuff from 1 and 2D because it's not really germane to our conversation. And let's change this. And do it for our specific function. All right, so if I wrote this down right, we're gonna, well, this is what I'm gonna use. So we've got our temperature is given by xy plus 8z plus 20. And then our region in space it's another trapezoid. And this one, the equation of the trapezoid was 8x plus y plus z equals 1. So let me show you how I get the vertices and all that so that I can draw them quickly. So again, here's my x, my y, and my z. So all I do is I let two of the variables go to 0. to find out what the third one is. So for example, if I let x and y be 0, I get z equals 1. So that tells me that this is going to be the point 0, 0, 1. For the y, I let x and z equal 0. And again, I get 1. So this is the point 0, 1, 0. And then for the x, I let y and z equal 0. So I get 8x equals 1. Or x equals 1/8. So that's 1/8, 0, 0. That guy right there. So there's the triangular cross section or slice that we see from that plane. All right, so we ready to start setting the sucker up?
Yeah.
Okay, so our average value, it's going to equal triple integral of xy plus 8z plus 20. I'm going to go ahead and do, again, dz, dy, dx, because why not? So in terms of z's, again, the floor is the xy plane. The ceiling is this plane, which if I solve for z, is 1 minus 8x minus y. Okay, now I also have this little triangular region in the xy plane. Right, so that's the remaining piece. So if we do dy dz, we can use vertical integration man. So I need y equals. So let's take this equation. Let z equal 0, because we're in the xy plane, which then gives us y equals 1 minus 8x. And then lastly, we need our bounds on x, which are going to go from 0 to 1/8. So that's the integral on top. Right, we're adding up that function over the entire volume. So there's our function over the entire volume. But now we need to divide by the volume. So how are we going to calculate the volume?
So wouldn't we have to do the integral first?
What do you mean the integral first?
Like, won't we have to do this triple integral to find the volume? Or is it just the volume of that one plane?
No, so it is the volume of this region, the entirety of it.
Okay.
But that's not this triple integral. But it's, yeah, Victor just put it, it's the same bounds. So 0 to 1/8, 0 to 1 minus 8x, 0 to 1 minus 8x minus y. But now we're just integrating 1. So if you have like an average value problem, what's really nice is that the bounds that you set up for the one is going to be the bounds for the other. And that's the same if it was the two-dimensional, right? Because if you want the area of a two-dimensional region, you can use the double integral. I mean, hell, it's even the same for the single integral, right? Like think about it, we're integrating from a to b f of x dx, and then we're dividing by the integral from a to b of dx. Think about what happens when you integrate this. You get 1, or you get x, plug in b and a, you get b minus a. So it's always same bounds, it's just we're only integrating the differential.
Who figured this out?
I have no idea. I really don't know who did multiple integrals. who came up with the idea of doing that. I'll look it up though. I'll see what I can find out. But pretty nifty. Definitely is useful in lots of places. And what I love is that, like, you look at what it is for triples, and you can see that it's the same thing for doubles, it's the same thing for singles. We're just adding a dimension every time. And so when you add a dimension, you go from length to area to volume. I mean, it's kind of cool. All right, so I don't remember who asked for this one.
Yeah,
I
that's
think it was
great. Thank you,
Seamus.
Bruce.
You feel better about that? Okay.
Yes.
Cool. And I promise you're not the only one who wanted to see it.
I'm just confused about how, like, with the sorry, question 10, the pyramid where we're now the dv that we're doing, the function of x, y, and z is x squared.
Uh-huh.
I'm just like confused why we need to treat that one different than xy plus 8z plus 20. I get that xy plus 8z plus 20 is linear and x squared is nonlinear. Do you see my question?
No, I don't, because I'm not treating it any different. Do you mean the fact that I'm only using one integral as opposed to four?
Yes.
Okay, that's because of this surface.
Okay, it's the pyramid that makes it.
Right. This
Okay.
isn't a pyramid, right? This is a tetrahedron, but this tetrahedron, the way that it's set up, there is one roof and one floor.
I understand.
But think about being under a pyramid, right? So there's our pyramid. If you're down here, your head is bumping up against the face that's closest to us. But if you were to go to the back side, now your head is bumping up against a different face. And the same thing, like if we went to the right, we're hitting a different top versus to the left. And it's because we now have a different roof, a different ceiling, that we're running into that problem. Unfortunately, my house is very boxy. I don't have any slanted roofs. For those of you who are familiar with the college, think room E106, the main calculus room, and how that roof is slanted, but then it changes over at another point, and then it slants a different direction. If you're down there walking along and you are able to be like Integration Man and bounce your head all the way up, your head would have to swap being from one part of the ceiling to another part of the ceiling. And as soon as that happens, that requires a different integral.
I guess my question is, does the fact that for that question we're going to be dealing with x squared, does that change our bounds at all?
No.
Okay.
Doesn't change the bounds.
I understand.
Right? Like if we had exactly the same pyramid as the other problem, number 9 or whatever it was, if we had exactly the same pyramid, the bounds would still be the same. You'd still have, your y's, they're going to be trapped between y equal x and y equal minus x. Your x's are going to be going from 0 to 1 and, and so on and so forth, right? So like all of that would still be the same. It's just there'd be 4 different ceiling functions. And because each of those ceilings have a different function, those each need a different integral. Is that making a little more sense?
Yeah, it makes perfect sense.
Okay.
I would have been thrown off if x squared affected the bounds, but I'm glad it doesn't.
No, the function never affects the bounds. Like here we're integrating xy plus 8z plus 20. Another time we're integrating 1. But that didn't change the bounds because the bounds come from the region. Okay, so the region specifies bounds. the function comes from whatever the hell the function comes from. The thing about like multiple integrals, and this is kind of different than like single variable integrals. For the when you first learned integrals, it was all about the function, right? Oh my God, I have to integrate natural log of x. Ooh, what's the integral of secant of x? Oh, what's the integral of whatever, right? The bounds, you never even thought about them because they were just numbers. You just plug them in. It's not a big deal. When you go to double integrals or triple integrals, now it's all about the bounds. Now you don't care about the function, right? Like to me, for this one, the fact that this is the temperature function is really irrelevant to me. It's an afterthought. I get the bound set up and then I insert function here. Okay, yay, big deal. And so the bounds are where it's at, which is all from what is the region, which is why I stress picture the region. Try to get a hold of in your mind, what does this region look like? Because without that, it's going to be very tough to do this piece that's, like I said, like 75% of the battle. All right, so okay for that? Ish?
Yeah, ish, definitely.
Ish, definitely. I'll take better. Can we at least go with better?
Yeah, yeah.
Feeling better about it?
Better.
All right, cool. All right, so anything else from the homework? All right, well, hearing none, then I guess let's go to remind ourselves about how we deal with cylindrical coordinates. And then we'll look at what do we do with spherical coordinates. All right, so give me a second here and I'll head over to the whiteboard. So it's funny, earlier today in my other class, one of my students was like, the whiteboard is right behind your desk. We can see it when you're sitting there. How come it takes you so long to get up to the whiteboard? And I was like, okay, well, easy. But then I had to explain, I have to like move my computer from the desk over onto a chair so I can still see it, so I can read the chat boxes and blah, blah. So it's like, it's not quite as easy as it appears, but, or I'm just an old slow guy. Yeah, it's 6 of one, half dozen of the other. All right, anyway, so what we got to last time was seeing that sometimes these triple integrals are easier done in other coordinate systems. So again, just to remind you, we're going to be looking at, they're really the three, right? We've got rectangular, cylindrical, and we have spherical. So the rectangular, we don't really need to talk about. That's the one that you're used to. We do it all the time, right? So that's the V, which is a, let me just do this. So we've got f of x, y, z, and then we've got dz, dy, dx, or insert your favorite, right? And so, and then there are just some sort of bounds on these that are functions of x, y, and z and whatnot, right? So that was rectangular, no big deal. We're totally cool with that. For the cylindrical, We just kind of hit this one last time, but we saw that what we need to do is convert this function so that it's a function of r, theta, and z. And then we need to throw in there an r dz dr d theta. And the rationale for this r was the same as before. We saw that that manifested itself in polar because the little volume chunk required it, right? And so that got thrown in here. And then again, the bounds are whatever they are, but now these are functions of r and thetas, right? R values, theta values, and so on. So this second one is going to be especially good with circular stuff. If your region is circular or made up of washers or other things that are kind of traditionally polar, this is definitely the way you want to go. And so just to kind of remind you what we did last time, we were looking at that like ice cream cone kind of deal, where we had a cone that then on top of it was the sphere. This was the unit sphere, x squared plus y squared plus z squared equals 1. And then the cone was x squared plus y squared minus z squared equals 0. I'm pretty sure that's the one that we used. And so we set it up in rectangular. We saw that that was horrible, right? It was rough. We then set it up in cylindrical, and we saw that it was much easier because these surfaces got a lot nicer, right? Like this bottom surface, the cone, that was just z equals r. And then the upper surface was the square root of 1 minus r squared, which wasn't terrible, right? And so we were able to set that up pretty easily, and it wasn't terrible when we thought about it in cylindrical. All right. So let's do another example of cylindrical, and then we'll go and we'll derive spherical. All right, so in cylindrical, let's try this one. Let's find the volume and it's going to be the volume of the solid that's under the paraboloid x squared plus y squared plus z equals 25. That's above the xy plane and within the cylinder x squared plus y squared equals 1. And what we'll do is we'll set it up. We'll look at what it would look like in rectangular. Then we'll set it up in cylindrical. You'll see why cylindrical is the way that we want to do it. But we all clear with what we're going to try to accomplish. Yeah. All right. So let's try to picture it. So we've got a paraboloid, x squared plus y squared plus z equals 25. Let's rewrite that as z equals. So that's z equals 25 minus x squared minus y squared. So this is an elliptic paraboloid. So it's a bowl. It's circular cross section because the x's and y's are both 1. And it's upside down because of the fact that they're minuses. And the top of that bowl is up at 25. So if this is the xy plane, it's a bowl, an upside down bowl, and the top is up at 25. Okay. So if I were to try to draw that thing, and I'm going to try to draw that, it looks something like this. And that might be the best one of those I've ever drawn in my life. Everybody screenshot that. Mark this moment down in history. It's crazy. All right. Really, that just goes to show how bad I am at drawing stuff. But there's this picture. Now, we want to know the area under that and above the xy plane. But I don't want all of it. I only want the part that's within the cylinder, x squared plus y squared equals 1. So x squared plus y squared equals 1 is going to be a smaller circle in here. That's going to cut down through this. So basically, this is like a little can with a little curvy bit on the top. Or kind of looks like a bullet, maybe a little bit is another way to think about it. But we're looking for the volume of that shape. All right, so if we were to set this up in rectangular, this is what it would look like. You probably want to do a dz first. Since we're finding volume, it's just going to be 1. So we'll do a dz, dy, dx. The z's, we're going from the plane, the xy plane, up to this paraboloid. So 25 minus x squared minus y squared. And then for the dy's and the dx's, we need to think about the region over which we're integrating. So if I were to draw on the xy plane here, x squared plus y squared equals 1 is a circle. It's just the unit circle. So if I was going to do integration man, say vertically, his head is on the upper semicircle. His feet is on the bottom semicircle. So that means we're going to be integrating on top. It's going to be the square root of 25 minus x squared. On the bottom, it's the negative square root of 25 minus x squared. And then the x's are going to go from, or whoops, not 25, but 1. Sorry about that. I was thinking about the wrong circle. And then the bounds on the x are going to go from -1 to +1. So that's what this would look like in rectangular. No big deal, right? We got it. It's not that big of a problem. However, check out how much easier this is in polar. So if we go to polar, or in this case cylindrical, now we're going to integrate r dz dr d theta. Right, that r shows up because of the dv chunk. The z's, we're still going from 0, but now the surface, the top, is 25 minus r squared. Right, make that convert. And think about that circle. That circle, to get all of that circle, we need our r's to go from 0 to 1, and our thetas from 0 to 2 pi. So both this green integral and this blue integral are going to get us the same place. I think the blue one's going to be a lot easier. Right? When we integrate with z, we just get a z, so multiply that by r. Now we integrate 25r minus r cubed. No big deal, plug in 1s and 0s. Once that's done, we get a theta multiplied by 2 pi. It's going to be fast. And you can get that volume quickly, right? In fact, let's just do it real quick. So 0 to 2 pi, 0 to 1, we're going to get r times 25 minus r squared, because the z just gives us z. So integrating that guy, we're going to get 25 r squared over 2 minus r to the 4th over 4, evaluated at 0 and 1. Because remember, when I distribute, I get 25r and then r cubed. So plugging in 1, I get 25 halves minus 1/4, which is 49/4, I believe. And then when we integrate that, we just get a theta, which means I multiply by 2 pi. And so it's 49 pi over 2, which should be the same thing you get from this other one. But this is going to be way faster. The other one, the rectangular, if you were going to do that by hand, you'd have to use trig sub or recognize an integral of inverse sine, an integral that gives you inverse sine, which most of us don't see. This one, there was nothing fancy about it. It was all power rule. Anyway, so this is a really good example of one where going to cylindrical, well worth it. Well worth it. All right, so how are we feeling about cylindrical? Cool?
Cool.
All right, so most people like cylindrical, especially when you get into one of these situations and you can see clearly how much, how much faster it is, how like easier it is, but it's all because of the region. It's all because of this, right? If it weren't for this picture, we wouldn't know that cylindrical is what we wanted to do. All right, so cool. Now we've seen that, and we're already pretty familiar with the conversions, so from polar, so it's not that big of a deal. But now let's talk spherical, because spherical is a different creature, for sure, because we don't do two-dimensional spherical, right? Like cylindrical is basically polar extended z. So that's no big deal. But spherical is a whole nother story. So again, before we dive in, let me remind you the conversions for spherical. So here are your conversions for x, y, and z in spherical coordinates. So x is rho cosine theta sine phi, y is rho sine theta sine phi, and z is rho cosine phi. All comes from the geometry space, a little bit big, brings us those values, right? So basically what we're going to be doing here is we're going to be setting up an integral where now our function is a function of rho, theta, and phi. And really we need to figure out what goes in here. What do we put in there to go with our d rho, d theta, d phi? Okay, so the way to do this is actually the same way that we did it before, which is look at a little bit of a differential chunk here using the d rho, the d theta, and the d phi. See what that volume looks like, what that shape looks like, and actually calculate its volume. Okay, so let's just start with what that means. So remember what rho is. Rho is distance away from the origin. So a little d rho is going to give us thickness. just like a DR gave us thickness, right? So it's going to give us a little thickness of this chunk. So, oh, I just realized I gave you two d phis here. One of those needs to be a theta. So let's make the last one a theta. Whatever, it doesn't really matter. Okay, so let's think about what phi is. So phi is an angle from the positive z, right? So if we're at positive z-axis, that's 0. Phi is increasing. This is phi is pi over 2 down to phi equals pi, right? But that's phi. So a d phi is going to give us a little rotation this way. D theta is a rotation this direction. So that'll do the same thing. So for this piece, we're going to get a rotation up and down and a rotation side to side. That's our d phi and our d theta. And then d rho extends it out. Okay, I'm going to try to draw this. And I'm not very confident. But this is basically what we're going to see. Okay, so this is our d rho giving us thickness. This is our d theta. And then we need a d phi. So instead of that being vertical, it's going to be curved a little bit. I don't know that that's too terrible. But basically, the way to read all this is our d theta. This is our d phi. And that's our d rho. All right, so I don't know, can you kind of see that? All right, so the question is, what is that volume? All right, well, first of all, just to kind of imagine what this is, think about this as like a piece of a basketball. I think basketball is probably the best thing to picture here. Because the basketball has thickness. Not a lot, right? Like you think about a basketball, it's mostly air on the inside, and there's this shell of, right? This is that shell of rubber. That's the d rho. The d rho is giving us that little shell of thickness of the rubber. And then what we're doing is we're cutting out a chunk. So you can imagine we start with a d theta chunk. And we're going to cut off that d theta. So that's what was formed is a piece that looks like this. Think of it like an orange slice, an orange wedge kind of idea. Or if you are someone who's into like maps, geography, and that kind of stuff, think about lines of latitude and longitude. These are longitude lines. The phis are longitude lines. So like if you were to just start walking due north from Tahoe, right? You just start walking due north. Eventually you'll get to the North Pole. Or if you walk south, you'll eventually get to the South Pole. And the same thing's going to happen if we're not in Tahoe. Like if we were to go over to Denver, walk due north, we'd eventually end up at the North Pole. Due south, we'd come down. Right? So that's what a d theta does. Is it brings us onto this. So we've got a little bit of this chunk. And then the d phi, that's your change in latitude. So now I'm definitely talking to someone who does geography stuff. I don't know if you guys know this. I know some of you do. I'm really big into geocaching, which is where they're hidden out in the world, and you go and you find them using your GPS. you'd be surprised. They are literally everywhere. I have a few hidden on campus at the college. But pretty much anywhere you live, you can find these things. But regardless, it makes me really comfortable with latitude and longitude, so it's one of the reasons why I think about it this way. Okay, well, I want you to think about this. Obviously, if I want to find a volume, I'm going to need to know an area of this and then multiply by the thickness. Well, the thickness is going to be the d rho, and that's always going to be the same. But notice that the area is going to change. If I were to look at a d phi strip, say that wide, that area is going to be different than this area that has the same width or the same height, right? Versus this one. So I'm trying to set it up so all of the heights of these blue chunks are the same. But notice that the area changes. And it depends where we are with phi. The closer phi is to pi over 2, the bigger our area is going to be. And it has to drop to 0 when we're at either 0 or at pi. Do you guys know a function that starts at 0, gets back to 0 at pi, and is biggest at pi over 2?
Sine.
Yeah, how about sine?
Thanks.
Right? It's definitely going to be sine. Sine goes from 0 up to a max and back to 0. So in here, there's definitely going to be a sine of phi. So as we build this thing, there's going to have to be a sine of phi. So then the question is, okay, well, how much? Right? What is the multiplier on that? Okay, well, here's the other thing it's going to depend on. It's also going to depend on rho. It's going to depend on how far away we are from the center. Does that make sense? Can you see why that must be? All right, so think about this. Right, it's so it is kind of the change in the amplitude sign. That's what we're talking about. But think about this. So let's just suppose that theta and phi, we pick a theta and phi. Okay, so we're just going to go a certain theta, change in theta, and a certain change in phi. And we do that on a baseball versus a basketball versus the earth. Which of those is going to give us larger area? Well, obviously on Earth, right? And I apologize for what I'm about to say. So please just suppose that delta theta and delta phi were each 1 degree. Ugh, I feel dirty. Okay, so let's just say that they're each 1 degree. And I do this because we can think latitude and longitude. Imagine on Earth, you were to go 1 latitude and 1 degree longitude and look at the portion, the area, the surface area of the Earth in that chunk. And compare that same area to a 1 degree latitude and longitude change on a baseball. Actually, I don't have a baseball in here handy, but I have my trusty LTCC soccer ball. So let's think about that. Like again, so we're going to go 1 degree in each direction. The area on this thing compared to 1 degree latitude, 1 degree out there, incredibly different. And the reason is this is much smaller radius than the Earth. Okay, so we know that it's going to depend on rho. And somebody started saying something, and I apologize for talking over him.
I was just gonna say the Earth's huge. It's way different.
Right? And so clearly radius matters. Well, think about this. Basically, we want to know the surface area. Well, surface area doesn't just depend upon the radius of the sphere. It depends on the square of the radius. Right? Think about just the formula for radius, 4 pi r squared, right? So not only is there going to be a rho in there, there's going to be a rho squared. And that's going to account for surface area. Basically, the reason there's a rho squared is if you think about the three sides of this that we're calculating, the one side, the d theta, that spread depends on rho, right? The further out you go, the bigger rho is. Good old S equals R theta kind of business from trig. And then the same with the phi, that's going to depend on rho. So each of those has a rho in it. Rho times rho is rho squared. All right, well, it turns out that that's it. That's the extent of what we have to put in here to account for this change in volume. So this is where the first place where this isn't nearly as nice as what we were doing with cylindrical. Right? If cylindrical, all you got to do is put in an R, no problem. Now with spherical, we have to put in a rho squared sine phi. Just because that's what it is. That's how these little volume chunks are created based on these three variables. All right, so in essence, what we have to do is convert our function with the x, y's, and z's. Then we have to put in a rho squared sine phi as we put in our d rho d phi d theta, or d rho d theta d phi, or d theta d, whichever of the 6 ways we want to do it. We usually do rho first, then we do the other ones. It just kind of depends on how we're feeling and what the shape looks like. We'll see later when we talk about doing a change of coordinate system to any old coordinate system. Like I hinted, the name is called the Jacobian. When we talk more about Jacobians, you'll see why this rho squared sine phi also must be, but you can reason it out from geometry as well. All right, so here's what I want to do. Let's go back to that same example, the ice cream cone shape, and let's set it up in spherical. So again, here's our picture. Right, we got that cone with the ice cream on top. We're trying to find the volume. Okay, now since we're trying to find the volume, that means our function is 1. So we don't have to do any kind of a conversion. It's going to be 1 times rho squared sine phi. I'll leave the d rho d phi d theta stuff for a second. Okay, so now we got to think about integration man. So integration man here is kind of like man in polar, where if we start with rho, which is what I want to do because it tends to be east way, integration man is going to be on radial lines coming out of the pole, out of the origin. Now these are 3D radial lines, right? So you can, go any direction like that, as opposed to just 2-dimensional radial lines. So if you were to send out some radial line here from the origin till it eclipses the surface, there would be one integration man, one example. Here's another one. Here's another one, and so on. Right, and all of these, you're kind of seeing him reach the topmost, but remember, he can also tilt in and out of the board. So when you're in spherical, integration man's had one too many root beers. He's a little wobbly, right? Because he can go in any direction. He can lean this way or that way, right? And he does. He leans all these different directions. And we're always paying attention to where is feet, where is head. So in this example, his feet are always going to be at the pole, at the origin. There's no way that as he's kind of moving around in this ice cream cone shape, that his feet are anywhere other than at the base. And then where's his head always going to be?
On the ice cream sphere.
Yeah, up there on the sphere. All right, so in terms of the bounds on this, his feet, they're at the origin, that's 0, and then his head is at the sphere. Well, what's the equation of his sphere in spherical? You're going to love this one. It's just rho equals 1. X squared plus y squared plus z squared. I didn't give you that conversion. That's the other direction. X squared plus y squared plus z squared is equal to rho squared. So for a sphere, you've got x squared plus y squared plus z squared equals r squared. Well, if that equals rho squared, then rho is just the radius. So in this one, integration man never changes height. He's always 1 unit tall. Well, that's why this is called spherical coordinates, by the way, because you can define a sphere really easily in spherical. Just like you can define a cylinder really easily in cylindrical. Cylinder is just r equals a number. Spherical is rho equals a number. Okay, so there's his rho, which is 0 to 1. Okay, so now let's talk phi and theta. I think theta might be easier because theta is the spinning around this way angle. And what angles is theta going to take on? All right, cool. Victor just put in the chat 0 to 2 pi. Right, as integration man here is wobbling around, he can go all the way in a full circle, 0 to 2 pi, because of the symmetry. So I'm going to do, yeah, we'll do that next. Why not? So we'll do d theta, d phi. So the theta is going to be 0 to 2 pi. All right, so the last question then is, what about phis? What are the different phi values he can take on? Now, phi is the tipping over bit, right? Theta was the moving around in a circle. Phi is the, oh, how far do I tip over, right? So at some point, he's going to be nice and erect, straight up and down. But he's also going to tilt.
Doesn't he tilt on the top of that sphere?
So he's going to start nice and tall right here, right? And then start tilting, 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 tilting. And the furthest he's going to tilt is when he is kind of like resting against the cone. So the question is, what are the bounds on phi there, right? Because this is the smallest phi, is straight up. biggest phi is when he's tilting. So the question is, what is that range? Well, smallest is 0, because if he's standing straight up, he's not tilting off of the z-axis. So that's an angle of 0. Okay, hold on a second here. So Victor just put in the chat box. I got to go look at my computer a little bit closer. Cosine inverse of z over the square root of x squared plus y squared plus z squared, followed by a question mark. Okay, so I take it you got the from the conversions, right? That we know that we can get phi using the cosine of phi business. That would work. That can work. I'm going to recommend that we don't do it that way. I recommend that we just use, well, trig. Let's use trig to help us out. Okay, because here's some things I know. Right, like basically, I want to know what this angle is right here. Right, I need to know this phi. But notice that I do have a right triangle here. And I definitely know one of these sides. Let me erase this a little bit because it's not part of the triangle. But which of those 3 sides do we know right now?
The adjacent.
One of them you shouldn't even have to calculate. What do you mean by cylinder?
Like the height.
The cylinder side? Do you mean this side right here, Victor? Yeah, okay. So what length is that? Yeah, it's just 1. It's the radius of the sphere. Right? This is going from the origin out to the sphere. So that's its radius. So that's just length 1. So all we got to do is figure out one of the other lengths, and we'll be good to go. I'm going to suggest that we find z. Because check this out. Basically, we need to figure out where the intersection of the cone and the sphere are. The sphere was x squared plus y squared plus z squared equals 1. The cone was x squared plus y squared minus z squared equals 0. So if I want to find the z, because the z is that vertical side, I'll just subtract. So I get 2z squared equals 1, z squared equals 1/2. So z equals root 2 over 2. There's a question forming, I can tell. I don't know who-
That's root 2 over 2, not 1 over root 2.
Same. It is the rationalized form of it.
Oh, I see. Yep.
To be honest, I go here just because when I learned trig back in the day, we were forced to rationalize everything. So I recognize root 2 over 2. But yeah, it's 1 over root 2. It's the same thing. All right, so in this triangle, this is 1. This is root 2. Is that enough for you to tell me what this angle is?
Pi over 4.
Yeah, it's pi over 4. if you don't see that that's pi over 4, you can use the inverse cosine. And when Victor put that big thing in the chat box, that inverse cosine is z over the square root of blah, blah, blah. Yeah, that's this. This is the z. This is the square root of x squared plus y squared plus z squared. It's just we didn't have the coordinates of that point, which is why that conversion didn't really help us, as opposed to just kind of drawing the picture. So now then we know that the phis are going to range from 0 to pi over 4. 0 is when he's nice and tall, and pi over 4 for when he's tilted as far forward as he can, as he's face planting into the cone. Okay, so he goes from 0 to pi over 4, and he does that in every direction. But remember, that's what the theta took care of. And then the r being from 0 to 1, saying that we get all of it, or the rho being 0 to 1. If we weren't filling in this entire thing, but we were looking at just like a shell, our rho wouldn't be all the way from 0 to 1. It'd be from A to B. Or if we were only going to do like half of this, our thetas would only be from, say, 0 to pi. Right, so those could change, but because we're doing the fulls, thetas are 0 to 2 pi, and the rho is going to be from 0 to 1.
Would it be wrong to say that the phi is from negative pi over 4 to pi over 4?
Yes, because phis in cylindrical or in spherical are defined as 0 to pi.
Gotcha.
Yeah, because there really isn't like a negative isn't necessary because it's the same as a positive phi. You're just going in a different theta direction. So we define phi just to be between 0 and pi. All right, well, this is also going to give us this volume. All right, now, before we, let's go calculate it. Let me show you how fast this is. So we're going to start with the rho. It gives me a rho squared. Integrating that gives me rho cubed over 3, which at 1 and 0 gives me 1/3. So I'm going to get 1/3. Integral from 0 to pi over 4, integral from 0 to 2 pi of sine of phi. All right, integrating thetas gives me just a theta. Valued at 0 and 2 pi gives me 2 pi. So this gives me 2 pi over 3 times integral from 0 to pi over 4 of sine of phi. Okay, well now we're going to go ahead and integrate sine of phi. That gives us negative cosine of phi. When we put in our pi over 4 and our 0, we get 2 pi over 3 minus root 2 over 2 plus 1. And so if we just sort of combine that all together, we get 2 pi times 2 minus root 2 over 6. And that's how much ice cream fits in that cone. And if you go back and you look at the one in cylindrical, I don't think we actually calculated it. I think we just set it up. But if you calculate it, you should get the same value. All right, so let's just assess this for a second. Let's just kind of look at this and think about what happened. Let's start with after we got it all set up. When it was actually time to do the integral, Hopefully you see this integral was nice and fast. Super easy. No big deal. Just flew right through it. All right, so that's a huge plus for these, is that for certain shapes, like this one specifically, super easy. Super easy to do the integral. Okay, but downsides to it. One, well, we get that rho squared sine phi thing, which is not terribly pretty, can be a challenge, but you know, it is what it is. But more of an issue is actually picturing the bounds. And I think the one that's most challenging is actually phi. Most people don't have too much trouble with theta because we're kind of used to the thetas, right? Because we did that with polar and we kind of see that. The rho usually isn't too bad because it's a similar idea to the r in polar. But the phi is weird. And that's going to be the one that gives you the most trouble, no doubt. But in a situation like this, it makes the integral super simple. All right, so basically take this for what it is. It's another way of setting this up with different variables, with different coordinate system that can be faster. And in a couple of sections, we'll make this generic. We'll just go to, well, suppose you were to transform it to any kind of coordinate system. How do you find this Jacobian? How do you find that little multiplier so that you can do the integrals? Because sometimes changing your viewpoint can make the integral way easier. And that will make a lot more sense when we get to those sections. But I see we're out of time, so I'm going to stop here. What I want to do next time, because I got to show you this, I want to show you how we can get the equation for the volume of a sphere. You may have done that back in, Calc 2 when you were doing, like volumes of solids of revolution and stuff like that. But I want to show you how we can do that using triple integrals in spherical coordinates, and it's fast. It's crazy fast to get the 4/3 pi r cubed. So, but we'll do that next time because we're out of time. All right. So other than that, don't forget you got homeworks that are due tonight. Make sure you get in there and bang them out. I think the last one is just plain old triple integrals, not the converting to cylindrical and polar, or cylindrical and spherical. That will be for next week. But make sure you get in there and work on that. All right. So anything else? Any other questions before I turn off the recording?
I have a quick question. So all those geometric formulas for like volume and surface area, do you think those were found geometrically first, or they were found via calculus?
There's going to be a mixture to those.
Okay.
Some of them, like the area of the circle, was long before calculus. Long before calculus. But I'm going to guess that a lot of the three-dimensional stuff was only known when this came around, or only like proven, right? They may have I don't really know, but I wouldn't be surprised if the Greeks had a pretty good idea of what the volume of a sphere was. They may not have known exactly, but then the calculus would have ended up proving it later. But that's kind of a hard one to answer. I'm not really sure. I'm not that versed on that to the history of math.
I got one more question for you.
Sure.
So I was playing with bubbles yesterday,
Okay.
and they look damn near perfectly spherical. Do you think they are? Like when
No.
the gases inside expand, do you think it becomes perfectly spherical?
No, I don't think they're perfectly spherical, mostly because of gravity.
Ah.
And the surface tension is not going to be the same everywhere. So I don't think they're actually spherical. I know for sure that the thickness isn't consistent. You know what I mean? They're not spherical shells.
Yeah.
The D rows are not the same everywhere because it collects more at the bottom. Like if you were to look at the thickness of the film, it's on the bottom than on the top. And I'm going to guess that because of that, it also leads to not being perfectly spherical.
That makes sense.
Kind of like raindrops. When raindrops fall, they're not spherical, but that's more due to lag. But yep. Love your questions, Bradley. I love them. All right, well, I'm gonna stop recording here.